All right, what's going on, everyone? My name is Ryan Perry. I am an engineering director for the Pyroscope team, and today we're going to be talking about building scalable OSS observability with Mimir, Loki, Tempo, and Pyroscope. It is a mouthful. As you can imagine, this is definitely a very big topic to talk about. We have 4 very sophisticated databases. There's a lot of really cool features that we've built into these, and so we're going to try to do our best to get through as much of those as we can today in just a short amount of time. So with that, let's go ahead and get started. What better place to start than with Hello World? This is probably one of the first log lines that many of you ever logged. Any of you ever started your programming journey as well as your observability journey. While it's small, I definitely think that it's something that a lot of people find familiar. If you're like me, there was probably a honeymoon phase where you spent a lot of time writing logs in those early days. There's definitely this kind of one-size-fits-all solution mentality, I think, for a lot of people. I know I spent months finding very creative ways to aggressively log anything and everything that I could in trying to solve any problem. There's this phrase that when you have a hammer, everything looks like a nail. And I feel like this graphic kind of nails those early experiences where no matter what the issue was or how big it was, what the nature of it was, you would find some way to try to do logs to fix it. But just like most of us outgrew the Hello World logging. We also sort of evolved our code practices, writing much more complex code than that. We also evolved our observability practices, doing more than just this kind of simple logging locally. You expand into more sophisticated logging techniques, collecting them maybe in Loki or something like that. But then also maybe even moving on to other signals like metrics or traces or something along those lines. The problem with using these logs so aggressively is that it's something that just doesn't scale. If you continue to try to log everything to solve your problems, theoretically you can do it. You could do metrics with logs, you could do traces with logs. If you're creative enough, you could do profiles with logs. But in reality, that's going to introduce a lot of inefficiencies and complexities and a lot of cost into your system that otherwise would be unnecessary. And so it's kind of like that last picture where you're trying to use a hammer to build something when you have access to an entire toolbox of things where there might be something that's more specialized for the specific task that you're trying to do. And so this is a challenge that's not only unique to logging, but it's also using any of the signals in isolation, whether that's metrics, traces, profiles, whatever it is. It's something that we often see people try to do. They get one thing, they're familiar with it, and they try to use it to solve everything. And again, if you're trying to do an analysis in this inefficient way, you're going to end up wasting your team's valuable time and likely valuable money as well. And so that kind of brings us to what we kind of see as the true definition of observability. And the idea is not just about collecting vast amounts of this observability data, putting it into a database somewhere, but also finding some way to answer new questions about your applications without having to write new code. And the way to do that is to kind of evolve past this idea of kind of like siloed data or, pillars of data and think of them rather than individually, but as a collective suite of data, a collective toolbox of things that, is better together than it is individually. And so as we as Grafana and then also our customers have started to scale, we've really started to understand the value of basically leveraging all this data across our different databases and getting some insights that convert into real business value on the opposite end for you all as users of the various Grafana products. And so today we're going to talk about what some of those features are that we've built and how those are basically geared towards improving your experience of making use of this data as you scale. And then not only that, but then also how you're able to then use these individually and collectively together in order to basically have a more comprehensive understanding of your applications. So let's jump in, and basically some of the core questions that came from you all, from a lot of our customers, and that kind of drove our product roadmap and the things that we've been building over the past year. For metrics, one of the big one is, how do I find anomalies in metrics trends? This is something that has definitely come up a lot. Metrics are notorious for having a lot of data, and trying to make sense of it can sometimes be a little bit difficult. And so finding anomalies in metrics trends, Loki, Tom talked yesterday in the keynote about needle in a haystack queries. We're going to talk a little bit more about that and how it works kind of behind the scenes, and some more details on when it's most useful. For traces, how do I find latency across where errors generate across multiple services? This is something that tracing is uniquely positioned to do. When you have a lot of different services, you have a long trace and you can figure out the latencies. And then finally, how do I find root causes of issues at the code level with profiling? We'll end with that. And so to get started, how do I find anomalies in metrics trends? First of all, if you're not familiar, Mimir is it's basically the central component for Grafana Cloud Metrics. It functions as a distributed time series database. And basically, it was primarily designed for Prometheus, but it also has support for open telemetry now. And it has all the features that you would come to expect from the various Grafana products: high availability, horizontal scalability, everything you see here on the screen. Most importantly, though, it has fast query performance, particularly as you scale. And then obviously you can query things quickly, but that's not useful if you're not able to analyze the results that come back in an efficient way. And so one of the features that we've built recently is the native histogram feature. And basically what this is a more advanced version of what existed as just sort of a normal histogram. You can kind of see the old version here on the top. On the left side, you would have to manually create the buckets that you were using for your histogram. And again, the goal of a histogram is to be able to show the distribution of your data so that you can see outliers and find, something that's particularly interesting that you might want to look into. And so, when you had to manually create buckets, if you did manually create them in a efficient way, and you picked good bucket sizes, then it looked great. But as soon as your data started to scale, then you end up in a situation where it looks like this top chart, where the distribution is not great, and and nothing really stands out in the heat map either. And so with the native histograms feature, basically, it's also in line with the open telemetry exponential histograms work that's being done. But the difference is that not only does it automatically choose the buckets for you as your data scales, it will continue to basically, kind of morph and readjust those buckets so that it's always adjusted to your data in a way where you can kind of see things that stand out. And as you can see there, the histogram, or the chart here of the distribution is much better there. And then, like I said, it's great to have that in isolation, but then, what do you do with that data once you've determined that something stands out as being an anomaly or an outlier? We also have this exemplars feature where you're able to then go from this outlier, metric to a exemplar, to a trace that corresponds with that. And so it kind of, again, brings everything together where it's better not just in isolation, but then coming together. So native histograms in Mimir help you find anomalies as you scale your data. We've also added a lot of features to Loki for finding needle in a haystack with log queries. And so next up, we have Ed, who is going to talk a little bit more about needle in a haystack queries as you scale.
Thank you, Ryan. So I'm Ed. I'm the Ed that Tom was looking for yesterday. So if you want to talk about adaptive logs, you can find me. I've got this brand new Loki shirt that I made yesterday. But I'm not here to talk about adaptive logs today. I'm here to talk about Loki 3.0. First, I kind of want to give a little bit of a history around Loki. So believe it or not, Loki was announced in 2018, which was 5 years ago. I struggle with this sometimes because that both seems like an eternity ago and really not that long. But the history went something like this. We announced, 2018, Loki's announced A year later, 2019, we said Loki is production ready. The APIs were stable. We were consistent in it, or comfortable in its performance and consistency, and we wanted you all to start using it the way we were using it. But it was really in 2020 when we introduced LogQL v2 that Loki became the product that it is today. So this allowed us to take Loki's simple data model, which is in just a string, probably its biggest strength in my opinion, because it easily fits into your environments with your applications that have all kinds of data types and log types that are structured and unstructured, and ingest all of them very easily without having to figure out schemas or anything up front. And then at query time, we can parse those to pull structure out that allows us to, do analysis on the queries, to be able to turn them into metrics and be able to filter and do the sort of, schema at query time stuff that we do with Loki today. And then interestingly, we didn't do a major release for the next 2 years. We did a lot of work. We added a lot of new features, but they didn't really feel like they had a sort of major rev version to them. So maybe one exception to that is the TSTB index. Quick show of hands, who runs Loki here today? Yeah, let's go. So if you're not using the TSTB index, you definitely should. It was a huge improvement for Loki in terms of our ability to plan query performance and query execution. Anytime anybody comes and asks me, how do I make Loki's queries faster? The first question I'm going to ask you is, are you using the TSTB index? I'm getting ahead of myself, but definitely TSTB index, way to go. Probably should have been a 3.0 around that alone, but we didn't. So here's where we are today, working extremely hard to build Loki 3.0. AI has made building slide decks extremely fun for me now. Particularly, I enjoy the prompt part of it, so I always include the prompts on my slides. But here we are with Loki 3.0. Early next year. It's close. We're getting there, but we got some work to do yet. So if you can't wait, there is going to be some things coming in December, which I'm really excited about. So I've been working on a series of blog posts to try to sort of catalog what we've learned about building and running Loki over the last 5 years. So things about, how we run it internally at Grafana Labs, how we size our machines, how we run them, how we scale them, parallelization settings, configurations, how we build cache, retention, a lot of stuff that is a bit sparse to find in the documentation today. We're going to do a set of blog posts around that to kind of, kick that information off. That will make it into the documentation that becomes part of 3.0. Look for that in, say, mid-December timeframe, around the 5-year anniversary mark for Loki's announcement. Back to the 3.0 announcements. Loki 3.0 will have a native open telemetry endpoint, so you can send OTLP directly to Loki. To accomplish this, it's a bit interesting. We extended the data model, which was just a string, by also supporting some key value pairs and structured data. So the open telemetry protocol comes with metadata associated with it. Currently, the collector will let you handle this by serializing that data into the log line. However, that gets a bit messy at query time. It's not the experience we really wanted, so we made a place to put some structured metadata. This also exists in the API for Loki now too. So like with the Grafana agent, you can use this to store data. There's some interesting applications for this. This data is not indexed. An example I might give is a pod label in Kubernetes. A lot of times this is fine as a label, and a lot of times it's useful to kind of understand, the sequence of events that happened in a specific pod. But when you run like work scheduling environments or have really ephemeral pods that churn all the time and you get up with thousands or tens of thousands of pod labels, it really beats up Loki's index, and kind of didn't have a great solution for that. You could find a way to stuff it into the log line, but that's a bit weird and a bit cumbersome. So now you can use structured metadata to be able to store these, sort of metadata key value pairs in a way that's not indexed, but it still allows you to filter them, but doesn't explode Loki's index and makes it a lot happier. So excited about that. And then the last thing I'm going to mention is the part that I'm excited about, which is we're going to do a bit of overhaul in Loki. So we're kind of going through and cleaning up what is 5 years of very aggressive, very fun development. So fixing a lot of configs that are inconsistent, like around object storage, where we have sort of S3 configs that really aren't the same between like the way we do storage of chunks and alert manager rules and things like that, or alert rules. Getting metric names consistent so that they're all prefixed the same way. These are a bit disruptive changes. I apologize for that for all you running Loki, but really this is how we set ourselves up for basically what is now the next major milestone of Loki, which is its maturity as a project. So, I think in many ways, it's not like feature development will slow down. We're just getting more targeted with what we're building and why. And a great example of that is the query acceleration that we're putting. This is the flagship feature in Loki 3.0. And I'm going to hand this over to Vlad to talk about essentially why we're doing it and why it's so important for the project.
Thank you. Hey, everyone. We all love when the query runs fast, don't we? Loki already runs it extremely fast. It can process about 1 terabyte a second for a single query. Our Grafana Cloud's client queried tremendous amount of petabyte logs a day. And it's interesting that for about 50% of analyzed data, Loki returns no results. Of course, we see a lot of non-optimal queries, but also we see that sometimes our clients needs to find the needle in a haystack. For example, imagine a client wanting to investigate a failed order without prior knowledge of where the relevant logs might be. They are forced to search the entire production environment. And what Loki does at this moment? It goes to the index and finds all the chunks for the requested matcher. Be sure it will be a huge count of the chunks, and one of the reasons is because Loki doesn't index chunks content. So Loki needs to download all of them and analyze logs line by line. Of course, this process is highly parallelized, but anyway, it requires a lot of computing resources. But what matters most is the client waiting for the results, the time the client waiting for the results. That is why Loki 3.0 will include query acceleration assisted by Bloom filters. Bloom filters are space-efficient probabilistic data structure for detecting if data doesn't exist. In other words, it will help Loki to know where it should not search for data. This aims to reduce the cost and latency of finding needles in a haystack by up to 1,000 times. Techniques like Bloom filter have historically been difficult to adapt to Loki because Bloom filters requires keys to index and look up, but Loki doesn't enforce structure on the logs. The ability to ingest logs from different teams, from different applications, has always been one of Loki's strengths. So it can be anything, log.fmt or JSON or unstructured text. Fortunately, Ngrams doesn't require to understand the format of the logs. Using this solution, Ngrams are just the sequences of adjacent characters. And using this solution, we can extract the keys from any string and ingest those into specialized Bloom filter. So after this, when the user runs the query, Loki understands if it can accelerate it using the new approach, and it does it. This solution doesn't require to change the query or update Grafana dashboard or alerting rules to start using the acceleration boost. Here you can see that Loki splits the ID from the line filter to all possible combinations of ngrams, and they will be tested against the Bloom filter to check if the chunk might contain the data even before downloading it. There are many variables in play to calculate the effectiveness of this approach, but we can already say that when we run a query with a short line filter, this solution reduces the chunks count to check by 72%. And for the long line filter by 93%. And when we run a query with a line filter with lengths like UUID, this solution reduces chunks count almost by 100%. Of course, Blooms are not free. They cost money to create, store, and query. However, at very large scale, with the heavy needle in the haystack workloads, they can save substantial money and latency by significantly reducing the amount of data Loki needs to scan. As I mentioned before, our experience running Loki sees about 50% of data processed and returned no results. That is why we are so excited about Bloom filters. The potential to reduce the amount of data Loki needs to scan between 70 and almost 100% is really exciting, and it will improve operational stability and will give us a completely new query experience. And it's important to note that this solution doesn't require any additional user's complexity in fiddling with what data needs to be indexed and how to query it. Loki will continue to work the same way it always has, just faster and more efficiently. Yeah, and now when we've discussed the improvements we've made for the Loki, I'm really happy to invite Mario to talk about Tempo.
Thank you, Vlad. Hi, everyone. I'm Mario. Next, I'm going to be talking about Tempo and how some of its new features can help us find where errors and latencies originate across services. But before that, a quick recap. So Tempo is Grafana's distributed tracing database. And earlier this year, we unveiled Tempo 2.0, and with it, TraceQL, Tempo's native query language. With TraceQL, you're able to search for traces based on the data and metadata. So let's quickly go over what a typical TraceQL query looks like. So what you see in the screen is a set of conditions within curly braces, which basically means just find me traces that match those conditions. We have at the top resource service name equals app food. That's just the name of my application. Then we were using a regex matcher to match a specific URL path. And at the bottom, we are searching for a range of HTTP status code. So anything above 100 is an error. So we're looking for those. Right, so now that everyone is at least a bit familiar with TraceQL, I want to highlight some of its two of its new features, which are metric summaries and structural operators. So let's go over a problem and see how they can help us. So say I'm a developer or SRE or a similar role, and I know that a service within my system has an elevated error rate from an alert that I just received or from some metrics. Following the example query we were seeing before, we could easily translate it to something like this, right? Resource service name equals server, again, the name of my application. Within that application, we're looking for errors. And we could already feed that to Tempo, and we would get results back, a list of traces that match that criteria. Now, what you typically would do is you would open a trace, then another one, searching for attributes and variables that correlate to the issue that you are investigating. Now, what you could use instead is use metric summaries, aggregate by variables that you believe or suspect could be relevant, and get that information straight away. So I know in my server, I'm serving an API. I want to check if there's any correlation to the different endpoints in my application. So what I'm going to do is aggregate by HTTP targets, which is an attribute in my traces. If I do that, I will get a table like this one, which contains a summary of my tracing data aggregated by that very variable that I passed. You can see at the left, there is all the different endpoints listed, and then we have different metrics, such as span count, that's the number of occurrences, the error rate, and different latency percentiles. So what I can do is, for example, sort by error rate, and on top of seeing that my server doesn't work very well, there's error rate everywhere. In particular, there is an endpoint/account that has a higher than normal error rate. Cool, but I can go one step further. So tracing is commonly used to sort high cardinality data, such as account IDs, user IDs, pod names, queries, basically anything. And one of the strengths of Tempo is that it is able to handle these very high cardinality data very well, even at query time. primarily thanks to its column-oriented storage layouts. I'm not going to go into detail about that, but if you're interested, then just find me after the session. But yeah, what this means is that I can take the previous query and aggregate by something like user ID and see if the errors are concentrated in a particular customer. What you see now on the screen is the amazing and fantastic query builder in Grafana for Tempo. What I'm doing at the top is selecting the name of my application I want to filter by, and immediately I get a TraceQL query at the bottom. So this is a great introduction to the language for anyone unfamiliar with it. Then on top of my previous aggregation I was doing before by HTTP target, that's the attribute for the different endpoints, I'm also going to aggregate by user ID. If I do that, I will get a new table, very similar to the previous one, but this time aggregated by both variables. So again, I will sort by error rate, and I can see that within my /account endpoint, there is a particular user that is concentrated on the errors. In summary, with metric summaries and 2 quick aggregation, I've been able to discover 2 new variables that correlate nicely to the issue that I was investigating from my original starting point. This can be especially valuable as you scale and you grow and you have more services and more endpoints. Being able to get these summaries gives you a good high-level understanding of the health of your system. All right, now moving into the next feature, structural operators. So as those familiar with distributed tracing will know, traces have a key difference to other telemetry types, such as logs and metrics, and that's that they're structured. What this means is that as data flows through your system, distributed tracing propagates a context with which we're able to reconstruct the data into a tree-like structure like this one. And well, so far we've been using, or rather querying for individual units or individual measurements, like find me errors within this service for this API. But what we can do now with the structural operators is navigate that structure and use that structure as conditions for queries and find those very specific queries that we're looking for. So what does this look like in TraceQL? These are 2 examples of TraceQL queries using structural operators. In the first one, we're using the direct descendant operator, and we'll translate it into natural language to English would be something like what traces go first through service A, then through service B. But this is not limited to just services. You can query by any attributes or metadata within your traces. So we could build something like the query at the bottom, in which we're using the descendant operator. Translated again to English would be something like what traces go first through service A, then have errors. If you're using distributed tracing, it's highly likely that you will be running a distributed system. And with this feature, you're able to search for upstream dependencies and downstream dependencies of your services. Now, the cherry on top for the query is that I'm then piping the results using the select operator and bringing the name of the name of the services where those errors are occurring. So theoretically, I wouldn't even have to open a trace. I will get that information straight away in the list of results of traces that match that query. And well, we can apply that directly to our example we were seeing before. It could look something like the query at the top. We have resource service name, server, appears in all the queries. Then from the information that we got from metric summaries, we know the errors are related to specific HTTP endpoint. Then we could also put the user ID, but then the query wouldn't fit on the screen. And then finally, we're searching for errors in upstream dependencies of our application. Then we would get a list of traces those traces that you're very specifically looking for. But well, identifying where the issue is only half of the battle. The next logical question is almost always what code actually causes and how to fix it. And for that, I'm going to leave you with Ryan, who's going to talk about profiling and Pyroscope.
Great. Thank you. All right, I'm back. So what's going on, everyone? Yeah, so root cause, I guess before I jump into that, this is my first ObsCon, and yeah, I want to talk a little bit about the reason that Pyroscope joined Grafana, because it does kind of align with a lot of what we've been talking about today. Basically, I'm also one of the co-founders of Pyroscope, and so we had have a really great open source profiling project, and we have a cloud version as well. And basically, we saw a lot of our customers, both big and small, who were as they started to scale, they were really interested in the profiling data and getting a lot of value from it, finding root causes, but they really wanted to be able to connect this data along with their traces, metrics, logs, and we just felt that there was a way higher ceiling of the types of benefits we can give with profiling, where rather than it solely being its own kind of sandbox application, we could also integrate it in with other signals as well. And so I'm going to show you some of those examples today. But yeah, excited to be able to kind of raise the ceiling of the type of value that we can provide with profiling alongside the other signals. So in terms of the root cause piece, I would say there's three main areas that profiling really helps in solving the root cause of. The first one is cost cutting. I guess these are in no particular order, depends on what's most important to your organization. But cost cutting, you're able to get a really granular line level breakdown of the application and where your resources are going, whether that's CPU, memory, contentions, whatever it might be, and kind of get the resource hotspots, which often correspond to the cost hotspots. The next one is latency reduction. For a lot of companies, being able to reduce latency corresponds to being able to increase revenue. You can think, rideshare, fintech, e-commerce. The longer people are waiting for things, the more likely you lose out on potential revenue for those. And then incident resolution, being able to pinpoint the exact location of memory leaks, the reason for a spike in CPU, and also being able to see the code level details when debugging things, all are really good areas where profiling excels. So before I get into that, I want to just talk about what is a profile. How do you read it? When they get more complex than this, it can seem like a little bit intimidating. It can seem a little bit intimidating as a visualization type, but really you can think of it as just a giant kind of nested pie chart. So the way that you read this is that the width of the flame graph in a continuous profiling sense represents 100% of the time that the application was running for the time period that you're looking at. And then basically you read it from top to bottom. Technically, this is an icicle graph. We say flame graph because it fits better with the name Pyroscope, but flame graph is technically when it's inverted. But yeah, how you read this is that the width is 100%. And so here you see the main function is running two functions, do a lot and do a little. And then so you can see those are then each calling prepare for a different amount of time. And so you read it from top to bottom. Main calls do a lot, which calls prepare, and main also calls do little, which calls prepare. And then you can see the percentage of time that the application spent on those two functions, which again, if you translate this into a cost perspective, this means that, if you spent $100, 65% of those were spent working on CPU, 65% of that was spent on the do a lot function, and 26% was spent on the do little function. So now you know where you need to go if you want to optimize this application. In the incident sense or in, some other sense, same thing. You're able to see exactly where your resources are going. And so profiling is not a new thing. Profiling has been around since as long as coding has been around, but continuous profiling is kind of this new piece that has emerged in more recent years to be able to do this consistently over time, attach a similar level of metadata to these profiles so that it functions similar to logs, metrics, traces, the other signals that you're used to. And I can, if you want after this, find me and I can talk about how we're able to store, what looks to be more data than a log line or a trace, be able to store it really efficiently. There's a lot of ways you can take advantage of the structure of a profile in order to compress it really efficiently and store it over time. But I'll save that for later. The key piece to realize here is just that you have the two dimensions, the query and the query labels and the query time period. You have the resource usage over time, and then you have the flame graph. And so you're able to combine all of those to get continuous profiling and be able to see different dimensions of your data and broken down by flame graph. So this is one, kind of just visualizing the costs and how profiling, how does it actually help you cut costs? So basically, obviously we're in a different economic environment than it was a few years ago. I would say a lot more people have started to focus more on efficiency, especially from a cost standpoint. And profiling is really uniquely able to give you insight into your costs that other signals might not be able to do. And so, this is just kind of a theoretical example of some of the different areas where as you scale, from years ago to today, you have infrastructure, you have deployment tools, you have messaging and queuing systems, incidents, even your observability suite itself is generating some costs. And so basically what profiling is a very low overhead piece that you add to your application in order to basically break it down. You can, with 1 to 3% overhead, you're able to then get really granular insights into, maybe the example I mentioned earlier, someone left in one of those really elaborate log lines, and now you're spending, 10% of your CPU logging something that you don't actually care about. But those types of things you don't actually catch unless you have something like profiling to help break down, what's going on. The other one is revenue generation. Like I said, as latency increases, revenue often decreases. This is for a lot of this is true for a lot of different industries, fintechs, banks, e-commerce. And again, just being able to understand where that latency is going from a CPU perspective helps you break that down and ideally increase revenue as well. So now for the incident one, I'm going to show a quick demo, as this may be a lot of people's first time seeing profiling. So hopefully you all can see this well. I'll try to make it a little bit bigger. And so this is what profiling looks like. And I'm just going to go through a really quick example showing, how you might debug a incident that's happening. Let's say you were using, metrics or something, or even just looking at this page for profiles, and you've come to realize, let me refresh it here. You've come to realize that we're looking at CPU usage over time. We've broken it down by one label, and there's one particular region that's consuming a lot of CPU, right? You see here, the north region is consuming all of this CPU here, whereas the east and the south regions are consuming much less. Now, one thing that's useful about profiling is you can then go in, you can click on these individually. You can see the profile associated with each of them. And you could even get just like a really quick high level view of like, okay, I see that, this resource here, or this line here, is consuming 85% of this, green portion. But one of the things that's even more valuable about profiling is, now you can do a lot more operations with these flame graphs. So let's say we want to compare, why is the south region consuming so little, while the north region is consuming a lot. Go into this compare tags function. And so now we can actually see those two profiles side by side. You can kind of see here, this one on the left represents the south region. This one on the right represents the north region. And again, you have two different dimensions. You have the time dimension, where we can select different time periods here. And then you have the label dimension. So we could select, any combination of those two to see them. And side by side, you can see some difference between them. If this is your code, you kind of start to realize the difference between a healthy flame graph and an unhealthy one. Similar to as you look at your dashboards, you kind of, someone else who's looking at the dashboards you're familiar with might not see anything, but then you looking at them, you could tell immediately like, oh, that's, that particular metric looks different. The same ends up being true for flame graphs. But the really valuable piece of this is then being able to compare flame graphs from, again, either two different time periods or two different labels. And so here, what this does, if you go to the diff view, is it takes those two flame graphs we saw side by side from the last page, overlays them on top of each other, and basically subtracts one from the other. And then you get this diff similar to like what you would get on GitHub that shows you the difference of sort of before and after, and is then going to highlight the areas that are consuming significantly more resources in one and less resources in the other. And so now between that pie chart, the region that was consuming a lot of CPU and the region that was consuming a little, you can see here that the difference is that this check driver availability function was consuming 75% of CPU in one and 31% of CPU in the other. And now you're able to, if this is an incident where metrics might have just told you that CPU was spiking in that region, you now have a little bit more of a, kind of the root cause of that spike in metrics is specifically attributed to this particular function. Let's see, I'm going to jump back to the presentation here. Or actually, yeah, can you go back to the slides? And so that's just a quick example. We went through a CPU example. There's a lot, that you can do with others as well. Another common one we see is out of memory errors. Maybe you're using logs and you're able to see a spike in out of memory errors. Again, once you see that spike, you have to figure out what do you do with those errors. And so you can drill down and basically be able to see, okay, it's specifically attributed to this piece of the code. And then similarly with tracing, this is something that we've released into beta as of this week, the ability to have a profile per trace span, which is really useful. Again, you have some latency, you have some span that's slow. If it's something that's like maybe a DB call or something like that, tracing is going to be great at showing you that. But if it's something that is code related, you now go from being able to just say, oh, this span took 1.2 seconds to this span took 1.2 seconds and 28% of that was spent on this particular line of code or something along those lines. So as we've seen today, there's a lot of tools, as you scale, across all these different tools, there's a lot of ways that we've made it so that you can better find anomalies in metrics trends, find needles in a haystack, latency, root causes, and basically then also using these all together helps you to milk a lot more out of your observability suite. That's all I've got for today.